Welcome, everyone. The topic today is which GPU should I use? I am Paweł Pomorski. I am at the University of Waterloo with SharkNet, Compute Ontario, and Alliance. So the inspiration for this talk is the large variety of GPUs which we have accumulated on our systems over the years. There's 4 different major types and some minor types, and in the future there might be even more. And at this point, it might be causing some confusion to users. So this seminar will give a brief survey of what we have and what a particular GPU might be good for. Of course, it's useful to keep in mind that there's a wide variety of applications that run on GPUs, and all of you might be doing different things. And those different things might work differently on different GPUs. And I would only give 2 examples of an application in my talk, but the general advice to you is be aware of all these GPU options and ideally give all of them a try and find which one works the best for you. Okay, so let's survey first the GPUs we currently have. So the oldest one is P100, that's the Pascal generation, which was launched in 2016. That was followed by Volta V100 in 2017, T4, Turing architecture in 2018, and A100 Ampere in 2020. So how are these distributed among the clusters? As you know, we have 4 major clusters which contain GPUs. So this is Graham. The major card there is 320 P100s. It also has 144 T4 cards. So the T4 cards are a little bit unusual. I'll describe in a moment what they are. Plus, Graham has a small installation of the other cards, but it's not that significant. Then Cedar is our biggest in terms of the number of GPUs, though they are not the newest, 584 P100s and 768 V100s. Then Beluga, 688 V100s, and finally Narval, our newest clusters with the newest GPUs, 636 A100s. Now, the other 2 systems I will mention is Cynet Systems Mist, 216 V100 cards, but this is a system which has IBM powered 9 CPUs, so it has a different CPU architecture. And there's also the Rouge cluster, which actually has AMD cards, so MI50 cards. So I will not have a chance to talk much about AMD, and we have very few of those cards, but we might have more of them in the future when we buy our new systems. So that is something to keep in mind. But nevertheless, if you want to try AMD cards today, there is a cluster where you can give them a try. So the question then is, what are the differences between these cards? Here's one quick summary of differences. So clearly with GPUs, what you care about is the amount of numbers you can crunch, and the more, the better. And this table gives performance numbers, and I will discuss each column carefully in a moment. So first, let's focus on traditional scientific calculations. So, you know, the default precision for scientific calculation is double precision. So floating point 64-bit, where each number is stored with 64 bits in memory. So here's the performance for various GPU cards for this. So P100 has 4.7 teraflops. B100 basically almost doubles this, though not exactly, up to 7.8. T4 is a special case, and then 9.7 on Ampere. So we can see here the steady progress in performance as generations improve, except the T4 card basically has terrible double precision performance simply because T4 is meant to be a cheaper card to be used for a more restricted set of applications, and it doesn't really support double precision. So it can run double precision, but it doesn't have dedicated hardware on the chip to actually handle double precision. So it sort of emulates it, which is why the performance is so bad. So the main message here is, if you are doing double precisions in your calculations, avoid the T4 card. But otherwise, all these cards are roughly competitive. I mean, there is a factor of 2 difference between P100 and A100, but a factor of 2 is not that terrible. And then the other precision used for typical scientific calculations is floating point single precision. So floating 64, 32 bits for floating point. And here's the performance for this. So here's a 9.3 and then 15.7 on the V100, back to 8.1 on the T4. and then 19.5 on the A100. So again, they are roughly in the same ballpark. I mean, from P100 to the A100, you do get a twofold increase, but roughly the same ballpark. So, but the main performance, the main driver for performance increases in GPUs in this new field of machine learning, where now the GPUs are very commonly used, comes from these other columns. So because machine learning is such a significant applications for GPUs, the companies which make GPUs have started to add dedicated hardware to the GPU specifically tailored towards deep learning computations. And it is in this area where the performance gains have really come from. So if you are doing a standard calculation, the choice between the P100 and an A100, it's a factor of 2 in performance, roughly. So nice, but not totally revolutionary. You will see revolutionary increases in these other features. But the important thing is that even if you are running machine learning, to see those performance increases, your program must actually use those features. And it's not a given that it will. So if it doesn't use those features, then again, you will get comparable performance across all these 4 different types of cards. Okay, so the performance comes from the addition of these new units called tensor cores. So let's talk about them first. But maybe before we go to this, let's talk about precision as well. So traditional computing uses single precision for typical floating point calculations and double precision in engineering application where round-off error matters and so on. However, in deep learning, it turns out that you can get quite good results at lower precision. One possible reason for this maybe is because in deep learning, machine learning tries to emulate the way biological brains work. And our biological brains are sort of these messy, bubbly things where there's lots of randomness. In your neurons, they don't have to store connections between them to 32 digits of precision, and somehow they still work just fine. So when we do the mathematical analog of these type of operations, it sort of is intuitively clear that lower precision should be fine as well, right? So how do we lower precision? Well, we just use fewer bits to store information about numbers. And just to illustrate, here is the standard floating point. So floating point uses 1 bit to store the sign of the number, 8 bits to store the exponent, and 23 bits to store the actual digits, right? And how can you cut back on this? Well, one possibility is you can cut back on the number of digits you're storing. So you could use the full 8 bits for the exponent, but only 10 bits for the digits. And this is called TensorFloat 32. So this is actually a relatively new data type, only introduced in the A100 cards, so the latest ones. And the other possibility is you could use floating point 16. So here you cut back in both the exponent part and the digits part to 5 and 10. So you lose the precision, but because now your numbers take fewer bits, you can operate on more of them at once. So you can get more calculations done. And then there's some other types, which I won't discuss here, but for example, you can also store integers to fewer precisions where basically you have smaller range of integers and so on. So this is what precision reduction looks like. And then we also have tensor cores. So tensor cores are these dedicated units on the GPU, which are actually devoted to matrix multiplication. So matrix multiplication, that's all they can do, but they do it really fast. So if you're doing machine learning, you're doing a ton of matrix multiplications, so you're really going to benefit from those tensor cores. But of course, if you are running some other software which doesn't rely on matrix multiplications a lot, then tensor cores will not be of any use to you. So this is also an important thing to consider when you are using GPUs. So what do tensor cores do? Well, here I'm showing you what the first generation tensor core did. So this was a unit dedicated to performing the following operation. It would take a 4x4 matrix, multiplied by a 4x4 matrix, and the input matrices were stored in floating point 16, so half precision. And then it accumulated the result, and the result was either in floating point 16 or floating point 32, so in half precision or full precision or single precision. So so this was It's a very simple operation, but the main point of a tensor core is that the tensor core could do all of this in one go. So as long as so basically it could do it in a single cycle. So this is a significant gain in performance. So you have this quite rigid, quite limited scheme that it has to be only this operation. But as long as it is only this operation, it can be accelerated quite a bit. So this was the original tensor core, and actually later generations of tensor cores have been expanding the possible data types, and I guess matrix sizes as well. So on the A100, you can do a double precision matrix multiplication on a tensor core as well. So so back to these columns. So this is what the TC numbers correspond to performance you get from using tensor cores doing matrix multiplications. And for example, here the A100 introduces floating point 64, so double precision tensor core performance, and that gives you about a twice increase over the default double precision calculation, which means that if you are doing a lot of matrix multiplications and double precision on the A100, you might get some nice performance improvement, which you will not get on the other cards. And here is the floating point 32. As I mentioned, this is a new data type. This was only introduced on the A100. But if your calculation relies on, if you're doing a machine learning calculation, it relies a lot on this reduced precision type, then you will get a huge increase in performance. I mean, we are talking about 156, and then there's this additional trick, which is called sparsity. This is a kind of a controlled way in which you can zero out the insignificant elements of the matrix, so you can basically make it more sparse, and then you get double the performance on top of it. So I won't go into that much detail, but some deep learning algorithms can take advantage of this. And then this column is the floating point 1632 performance. So it's this performance doing this matrix and operation. And you can see that, you know, we go from 125 to 65 to 312. And again, let me emphasize the reason why this doesn't increase here is because even though T4 is a newer card, it was meant to be a cheaper card. So it has lower performance than the V100 would have, but you know, per dollar, it might give you better performance. And here we have, I just threw it integer 8 as well. So you represent your data as 8-bit integer. So, so the moral of the story here is that you have the tensor calculations are somewhat restrictive, but for certain applications, they will be of great benefit. And currently, these are mostly used in machine learning applications, but you could use them in other applications as well. I guess we haven't seen that many implementations yet, but you could imagine that if you are using some other calculation, even if you want a full precision result, full double precision result at the end, maybe there are some intermediate steps which you can use lower precision for and sort of accelerate your calculation. But this is the basic overview of what the performance is, which you can get out of GPUs that we currently have. So let me talk a little bit about upcoming hardware, because we are really hoping to refresh some of our systems in 2023. And because the P100 cards, for example, they have been launched in 2016, so they will be over 6 years old next year, almost 7 years old. And that's really pretty long in terms of age of computer hardware. And even though you are still getting nice performance out of them, as I've shown you in the table for conventional calculation, they are really going to be falling behind for the machine learning calculations. So NVIDIA has the H100 card. H100, very power hungry, uses up to 700 watts. It's already released. It might end up in our system. There's also a Grace CPU ARM architecture, which NVIDIA is also going to be making. AMD is now emerging as a serious competitor in the GPU field. So it has MI250 and 250X cards, for example, very strong competitors. So, and there might be newer generations released in the timeframe that we are acquiring new systems. There's also a new generation card in development, which could combine a CPU and a GPU. And Intel is also a player in this field. They are starting to make GPUs, though they are really a newcomer, I would say. And, you know, I think that ecosystem is still developing. But here are, you know, just a similar performance chart for AMD and upcoming AMD and NVIDIA cards. And I also put an A100 for reference, so that's the one we already have. So the H100 would offer, you know, a huge boost in, you know, floating point 3 times, floating double precision, single precision. and then also significant, even more significant boosts in machine learning. And then here is AMD. So AMD is actually doing great in sort of conventional double precision, single precision. It's highly competitive with the H100. So, and it also offers some machine learning features because it has what it calls matrix cores, which are the analogs of tensor cores, though it doesn't offer as rich a set of data types as NVIDIA does as of yet. And there's some other limitations of AMD, which I will not get into. And it is a newer ecosystem, though it has become much more user-friendly, I would say. And the development kit which they have is now very compatible with CUDA. There's still, like if you've been using NVIDIA GPUs for the last 6 years, switching to AMD might be a bit of a challenge for some users and hopefully very smooth for other users. So this is the overview. And at this point, I want to give 2 illustrations of the kind of performance you would get from these cards. So again, if you don't use this particular software, I can't cover everything, but hopefully this will give you an idea of how to benchmark your own programs and how to make, justified, reasonable decisions over which GPU to use. So the first example I will show will be Nnamdi. So Nnamdi is an MD code, molecular dynamics. So if you haven't seen such codes before, these codes are used to model biological systems most commonly. And in these models, you represent each atom, typically as a particle connected to other atoms via what are essentially springs. And you have a classical model where these atoms and molecules are bouncing around and interacting with each other. And if you run this model for a long enough time, and you can average it out and get some reasonable approximations of what a system, usually a biological system, looks like. So for example, in this picture, we are just modeling water, which of course is essential because biological proteins are always immersed in water typically. So here we have water molecules represented by 3 atoms connected by springs and interacting with each other through electrostatics and van der Waals forces. And then here we have a more complex system like a biological membrane where we have lipids with tails. Here we have this kind of a coarse-grained model where these tails would actually be made up of many atoms. Here they're just represented as rods. And the model which I will be showing you uses something like 500,000 particles. So it's a pretty challenging model. Now, the nice thing about molecular dynamics is that because these particles are jiggling around all the time, because the simulation simulates temperature by basically kicking each atom a little bit every once in a while, just to give it a random jiggle. That means that in practice, you don't have to store the atom positions to high precision. They can be stored with single precision. And so the whole calculation relies basically on single precision. That's not universally true in molecular dynamics, but in this case it will be. So that means that we can use a T4 card for this, for example, because Namdi should run quite well on it because it's single precision. And the typical message out of molecular dynamics is that, if you want to use more resources, make your system larger. So here, this benchmark uses 500,000 atoms. If I was using, let's say, only 50,000 atoms, I would have a real trouble using a GPU efficiently because I would just not be able to populate it fully. I would not be able to utilize it fully. So this is a very large benchmark in this example. So here are some performance numbers, and this is a rather busy graph, so let me talk you through it. So first, in this bunch of data, we have just the CPU performance, and this is basically 0 on this scale. So if you are using a single core, it just runs very slowly. Here is the one node performance without the GPU. So this is if we don't have a GPU and we just use all the cores on a given node, that's what we get. And these are results for the P100 on Graham, T4 on Graham, V100 node on Beluga and Narwhal node. But again, in this column, I am running without the GPU. So this is what I'm hoping to accelerate. Here is the example where I use a GPU, but I also use only a single CPU core. And you can see here that the performance doesn't actually improve. So even though I'm using a GPU, so what happened here? Well, that's because Nnamdi, at least Nnamdi 2.14, which I'm using here, So this is the latest stable version, which has been around for quite a few years, but still it is the latest version. Nnamdi uses both CPUs and GPUs to do the calculation. So some parts of the calculation are done on the GPU and some are done on the CPU, which means you need both. You need both enough CPUs and enough GPUs. They need to be balanced to actually work well. And here I just have too few CPUs per core, so performance doesn't improve. Okay, next column, I use a single GPU, and now I assign a certain number of CPUs to the calculation as well. So now I am doing the correct thing of having a mix of GPUs and adequate number of CPUs. And the number of CPUs in this case is just the number of cores per node divided by number of GPUs per node. So let's say when I have on Graham, I have 32 cores and 2 GPUs. Well, if I am using a single GPU, it's natural to use 16 cores. So the number of cores is different in this column for every case. But we can see that with a single GPU, we are getting a nice acceleration over the case either without a GPU or with a GPU, but not enough cores. And then finally, we have nodes with multiple GPUs in them. So why don't we use all the GPUs on the node and all the cores on the node? So this is the one node performance here. And you can see that we are getting even more speed up. But there's one thing which isn't looking right is let's just focus on habits on Narval. So on Narval, here's my 1 GPU performance, and here is my 4 GPU performance, because Narval nodes are very powerful. They have 4 A100 GPUs in them. So if everything was going well, I would be expecting a 4-fold increase in performance here, going from 3 to 12. And I'm getting nowhere near that, right? It's just basically the performance is stagnating. So of course, the main message here is I should never run Nnamdi on Narval in this configuration, because here I'm wasting 4 GPUs and I could get the same result using just 1 GPU. So this is something that you should always worry about when you are running, well, any kind of a program which uses multiple GPUs. Always make sure that using these multiple GPUs is justified, because there's really no benefit to you of using 4 GPUs here. You'll be using more resources. Your priority will be charged by using them, so you will be able to run fewer jobs. Your jobs will wait longer in the queue. It is just a terrible idea to run in this configuration. So always do some benchmarking to avoid that situation. So how can you do this benchmarking? Well, there's a new tool which we are slowly introducing. This is now open to users, so anybody can use it, but it's still somewhat experimental. We don't have it implemented on all clusters, so I guess we are not advertising it very widely yet. But here's a preview of it, and you can definitely try it. So for Narval, we do collect statistics for each job, and you can log into a portal and you can obtain some statistics. So here was my 4 GPU job on Narval, the Namdi job. So basically this column here, I am looking at the results of this job. In particular, there's the GPU utilization metric. And if you can see that my GPU utilization here is quite low. So when I'm running this job, I am only using 15% of the GPU. The reason for this is simply the A100 is so powerful that the work which I'm giving it to do is just insufficient. So especially when I have 4 GPUs. So if we compare this column and this column, here I'm taking the work that 1 GPU is doing, and I'm giving the same amount of work to 4 GPUs. And they just don't have enough. Utilization is very low. So this is the telltale sign that my problem size is basically just too small for the number of GPUs I'm using. And by the way, here we can collect a whole bunch of other metrics, which I will not get into today. You can also look at tensor core usage. So Namdi will not be using any tensor cores, but if you are using a machine learning, if you are running a machine learning program, you'll be able to collect these statistics. And also, this is just a single screen grab of a particular graph. There's many other graphs which are produced by this portal. So I might even show a brief demo of it at the end during the question time. So, so the basic solution, if I'm running Nnamdi 2.14 for this problem, I should not be using 4 GPUs. But the more fundamental reason why this problem is occurring is simply has to do with the fact that Nnamdi has, the way they designed their program, they are splitting the load between the CPUs and the GPUs. So what if you put all the load on the GPUs? Well, that would require rewriting the program, and that's actually exactly what Nnamdi is doing. So the Nnamdi has version 3.0 currently in the alpha release stage, so we can't really install it as a default module because we usually install only stable module. But this program has been redesigned to basically put everything on the GPU. So actually, when you run Nnamdi 3.0, you can just use one core per GPU, and this core is basically just used to control the GPU. It doesn't do any work. And you also have to put this option in your input file, CUDA SO integrate on, turn on the use of the GPU. And now what performance do you get? Here I am running one GPU with one core, and I get 7.6 nanoseconds per day compared to 3.1. So I'm comparing this column here. So just even on a single GPU switching to Nnamdi 3.0, I get a twofold increase in performance. But the really nice thing is if I now scale this up to 4 cores, I basically get linear scaling, which is exactly what I want. So my performance going from 1 GPU to 4 GPU goes up by a factor of 4. So basically, Nnamdi 3.0 solves the problem because it just completely switches over to the GPU. It does everything on the GPU. And then you get nice performance increases. You also save time in other ways. For example, the communication between the CPU and the GPU can be relatively slow because the bandwidth between the CPU and the GPU is limited. But now everything is on the GPU or on multiple GPUs, which still have to talk to each other, but GPUs and Narval are connected via NVLink, which is a very fast interconnect. So the moral of the story is, if you're using Namdi, you should consider version 3.0, which is still in alpha, doesn't implement all features, but at least give it a try, see if it can run on the systems that you're studying. And if you are using other software, you might explore later, some later versions of it. I mean, maybe a later version does a better job in implementing GPU usage because basically GPUs have grown so large that it's hard to fill them up with work. Quite often in fact, this is sort of our most common headache, that we have a lot of users who are using GPUs and their utilization is just low. They are not giving the GPU enough work. So for that case, either use fewer GPUs or look at versions of software which are more efficient in using GPUs, because they do exist. Okay, so and then let me move on to my second example, and this is looking at machine learning applications. Now, I am not a TensorFlow machine learning expert myself. In fact, I learned quite a bit just preparing this presentation, but I hope I will be able to show you something useful. But nevertheless, here I take a standard TensorFlow benchmark. I think this is the default benchmark they suggest when you install the performance testing suite, Perf0. So that's just the first one they suggest. So I run it, and the performance here, I guess it's the number of images processed per second. So this is ResNet is an image classification program. And we can see here that we actually have comparable performance on all the cards. I mean, T4 and P100 are obviously slower than the A100, but we are not talking about difference factor of 10 in performance or so on. I think this is because ResNet, it's a relatively old benchmark. It doesn't use any of the new features. So jumping back really quickly to this graph, I don't think it's, even though the output of the benchmark does say it uses TensorFlow 32 on the A100, we are not really seeing, these dramatic performance increases like, a factor of 110 or greater on the A100 versus the P100. So at least in this case, it seems that this benchmark doesn't use the advanced features which appeared on the A100 card and then earlier on the V100 and the T4. So the message here is that if you're using deep learning, you might benefit from using the A100, but not necessarily. If you are running machine learning which doesn't use advanced features like lower precision or tensor cores extensively, you might get quite good results running on the older cards. So, we only have one cluster with A100 cards and any great number, and they are under pressure. Lots of people want to use them. So if you find that your jobs are waiting long, you might be able to use those older cards. And there's one more thing I want to mention. So NVIDIA is aware that those GPUs, they've grown so huge, they are hard to use. So, I mean, they're hard to fill up with work. So one possibility is, why not slice them? Why not just work with a fraction of the GPU? And this functionality has appeared in the A100 cards, and these are called MIGs. So multiple instances of GPU, I guess that's what it stands for. And the reason this can work is, inside the GPU, you actually have what are called multiprocessing units. So these are like cores in your conventional CPU. So you can divide those cores up into groups and just give each job a different fraction of these groups, right? So in particular, on the A100, you can divide your work into up to 7 pieces. So this is not something done by the user. You cannot select this when you start your job. This is something that the system administrators have to sort of do a priori. They reconfigure the nodes. So let's say instead of a single A100 GPU, you have these 7 MIG GPUs. So they actually look like separate GPUs, but they are all actually one GPU. And if you can slice in different ways, so you can have 1/7 of a GPU, 2/7, 3/7, 4/7. So depending on how you want to do it. This is currently only available in NVIDIA GPUs as far as we know, not on AMD or Intel, but it might be coming. But we don't have this implemented on our clusters yet. So currently on Narval, you just use the entire GPU. But because of this low utilization problem, which many users run into, we are strongly considering partitioning at least some of the nodes into these MIGs. So how would this affect my application? But basically, we do have currently an experimental cluster made up of 2 nodes, accessible only to staff, where we can experiment with those slices of a GPU. And this is what I did for my example. So this is the same benchmark as before. And here is how long it takes to run it on the A100, the full one. And then I also ran the same example on the 4/7 slice. So this is 4/7 of the GPU, and then 2/7 and then 1/7. So as we can expect, as we are decreasing the size of the GPU slice that we are working with, our performance goes down. But the interesting thing is the line above is just the exact slice. So this is this exactly 4/7 of this, and this is exactly 2/7 of this, and this is actually 1/7 of this. And we can see that our performance actually exceeds the slice, right? So even though I am only, in this example, even though I'm only using 1/7 of the GPU, and actually, to be technically true, it's even less than 1/7, because there's a slight penalty to dividing the GPU into slices, something on the order of 10%. But nevertheless, here I'm using 1/7 of the GPU, so I would expect my performance to be here, right? But it's actually greater. So that means that the full calculation isn't actually using all of the GPU. Utilization isn't great. So if I give it only a slice, proportionally, I can get better performance than the slice would indicate, because this is underused. So unfortunately, I cannot show you the portal results for these jobs as I did for Nnamdi, because this is an experimental cluster, so we don't have the data collection enabled of it. But this is an example of what using MIGs would look like. So this would add some additional complexity to the cluster. But nevertheless, if you have a program which just doesn't utilize the GPU very well, you would not want to run it on this configuration where you're only getting 1/7 of the GPU. You would actually want to run 7 jobs at once, where each job uses only 1/7 of the GPU, and so gets nice performance.